Welcome back, everybody. So, last week we left off, I think I was working on the lighting subsystem, if I remember correctly, and I got that in and just building right now, and I'll show you what it looks like. Does not look nice right now because the rough goal for the next couple of weeks is, so lighting is in now, but there aren't any stylistic effects or anything, it's just basic Fong. Because my plan, I can show you what we're building, is to isolate, and this I've already done this, but isolate just the basic specular and diffuse components of each of my three lights into a function that I can then pull in at any shader that I want to. So I made this light influence struct that just has the color, the specular amount, and the diffuse amount for each of my lights. Then in any shader I want to use them in, like in the one shader we have right now, all you have to do is just include the lighting function and then iterate through each of our lights in our count and grab the light influence, and then from there you can insert whatever stylistic effects you want to be applied on top of the light. But for now, no stylistic effects. But anyway, the rough outline for the next couple of weeks is going to be lighting is in, and I'll be focusing on culling for a good while here. We have not feature parity yet, but we're actually now, before we get full feature parity, we're working on culling and performance in a way that we never had focused on before. So when we finally do get feature parity, we're actually going to be quite a bit ahead of where we left off with NC Graphics Original. And for those just listening in for the first time, we are building a game engine in C++. We've been working on it for 5 years or so, and had built the first render in Vulkan, but had a couple problems with it. We had even built our own custom physics solution and had a couple problems with that. So this time we've already pulled in Jolt, which is a physics API, or physics library, open source. And then we've also pulled in the Diligent graphics library, which is an open source kind of abstraction layer that abstracts over different rendering APIs like Vulkan and OpenGL and D3D. And it's also platform agnostic. So we're trying to get feature parity with what we had before for graphics right now, and taking a brief tangent to actually get more performance than we ever had before. So next couple of weeks, finish up lighting, which is, we're going to call it done, and then move on to culling, which is what I'm working on now. And I bet that will take me more than a couple of weeks. It's pretty much brand new territory for me. But after culling, I'm going to pull over our animation system that we had from Graphics 1, and that'll be easy now that we have our structured buffer in place. All I have to do, we already have the system. I don't think that much of that, if any, has to change. So I'm going to pull over our existing subsystem for our skeletal animation, and then all we need to do is throw in a different type of buffer and bind that buffer, and we should be good to go there. So after culling is animation, and then after animation, we are acquiring quite a bit of issues as we go along. And I don't mean problems, I mean literally GitHub issues I can show you. We're at 78 or 79 issues now. So I'll probably knock out a couple of those. Oh no. Oops. Alright, hold on a minute. I have to get my authenticator app going. All right. So after animation, which will probably be sometime mid-December, we'll get that in. Then probably knock out a couple of these, depending on where we land with performance, which is what Cal's working on right now. And then more or less... Oh no, I forgot about shadows. After animation is shadows, and that will take me a good couple of weeks, maybe a month. So that should put us somewhere around January, maybe February. We'll see. But knock out a couple of these, and then it's finally time to work on the shader and probably start game dev at that point. So very exciting times for us coming down the pike. Okay, so last week finished the light subsystem, made a nice, this is my first ever include file for shaders. Could never figure out how to do this before, and it can't say I tried very hard because it's actually completely trivial to do, but I'll show you my old shaders. I had so much duplicate code because I couldn't figure out how to do include files. So I had to redefine point lights, spotlights in every single shader, had the same shadow calculation functions in all my different shaders, had the same radiance functions in all these different shaders. It was a mess, but now I've unlocked the power of includes. But not a whole lot to see here. We just compute in the most simple of ways the diffuse and specular components for each of 3 lights. Some of them have attenuation, some of them do not. Throw them into a light influence struct, and then now the onus is on the shader to do whatever it wants with them. As soon as we're done installing here, which should be just another minute, I can show you what it looks like. It doesn't look good at the moment, but it doesn't need to. And I think I'm at this moment planning on calculating all of my lighting in world space, but because Cal's working on the matrix instance buffer, he'd asked me to wait on making the normal matrix, so we actually don't have a normal matrix that we're computing CPU side. So so the specular lighting is a little bit off, but we at least can see where objects are in the screen now. They are not all one color. So exciting, but not terribly. Got some new physics I've had for a while. Yeah, if you see when the worm rotates, you can tell that the normals are screwy because, let's see, we just had it when he fell off the bridge, but if a cube rotates, it doesn't respond to lighting correctly. Let's see, I think I got one. No. There we go, you can see it. This guy. Oh no! This guy right here. That's because of the normal matrix. I don't have it in. But that's fine, we made an issue for it. So today, it is brand new stuff for me. I've been doing a little bit of research, figuring out what kind of culling is going to look, what kind of culling we're going to try to do, what that's going to look like, and where that's going to plug in. But I thought today it would be fun just to try to get a compute shader doing something. I've never done a compute shader before. Don't really know where to start, but I'm going to struggle with that for a few hours, and you're welcome to join me. Okay. This is the Diligent Engine repo. I highly recommend this library. The creator is also incredibly responsive. I don't know how much time this person has, but they spend a lot of it just in a support role, which is awesome. Someone also managed to get code changes and features up constantly. Alright, I'm looking for an example of a compute shader in Diligent. I think he does one. He does. Be right back. All right. I would be lost without OneNote. If anyone has a good Markdown extension for OneNote, let me know, because I tried out OneMark and it's not really doing it for me. I really don't like OneNote's native syntax highlighting. It's absolutely terrible. So I think for this dummy compute shader, this first ever compute shader, I'm going to try to access the matrices buffer and move each matrix by some small delta randomly. So we can get some kind of pseudo animation just to see if this compute shader is working. So I'm going to need throw time dot delta time to the environment buffer. Do I need? I will need to make the object, the mesh renderer subsystem buffer, or mesh renderer buffer data buffer writable. Shader that runs prior to the material passes that each matrix translates randomly delta time. And writes. Hey, thank you for the follow. How exciting. That was startling. I've never had a follower before. Actually, I think I have one. Now I have two. So, if you just jumped on, I'm desperately struggling against trying to learn compute shaders. Because we're trying to cut over from just our standard Vulkan renderer that we've been working on for a couple of years to something a little bit more robust. So we pulled in the Diligent graphics abstraction layer and trying to get feature parity. One thing I've never done before, even in the old renderer, is have any kind of compute shader based culling. So we are diving into compute shader theory today. Now I'm flustered because I'm excited that I have a follower. Hey, Brian. Yeah, I don't think there's many of us, but Pirate Software is the main one. And he's huge. He's got like 50 or 60,000 followers now, or probably much more. And he's always really entertaining to watch. And he has a ferret rescue. That's pretty fun to watch too. Okay. What was I? Oh yeah, so we want to write the translated matrix back into the mesh renderer buffer data buffer. So some of this I can do right now. Let's tackle step one. So we need to get delta time into our environment buffer. So the environment buffer is the only constant buffer we have, but it just holds any kind of information that the entire scene needs. So the view projection of our camera, the position of our camera, and then just kind of housekeeping. So any kind of counts and indices that the shader may need for other objects live here. And if you're wondering what this padding vector is, you want to keep anything in a buffer, you want to typically aim for 16-byte alignment. So I can get rid of one of the floats in the vector. Now comes the fun part, trying to figure out at what point can I inject delta time into this buffer. It is, yeah. So this is C++, and we were pretty much just C++ and C makes the build system that we use, but most of what I do jumps between CPU and GPU land, and the C++ is all the CPU stuff. But what you're seeing today is trying to get, so we keep a concept of how much time has elapsed since the last frame in delta time, and you can use that to animate any kind of movement because that's your concept of elapsed time. And so what I'm trying to do is get that from the CPU into the GPU so that the shaders can read it. And I know you know some programming, but I don't know. I know Kate was mentioning that you know that you do programming. I don't know if you do it for your job or what you do, but that's pretty cool. So if this is all new to you or if you know all of it, oh sweet, yeah. I would be happy to say that I do C# for my day job, but I can't even claim that anymore. Yeah, it's rough out there for us devs. But I do VB for my day job, which is kind of the red-headed stepchild of C#. It's worse. It's rough out there right now. I was very, very lucky to get my job. I found that, so I've had like four different programming jobs throughout my career, and it's always been, up until this last year, it's been like, okay, I'm looking for something new. Within days of trying, I could get a job, but I decided I wanted to go back to work from watching my son full-time in May of this year, and I'm generally really hireable. And it took me grinding and getting really stressed out and really anxious, like 2.5, almost 3 months of straight interviews and applying and grinding leak code and all sorts of crap to try to get a job. And I was getting pretty depressed there for a while. And I think 3 months is pretty fast for people. I got lucky because I have contacts at my last job and they wanted me back, thankfully. But man, I've heard of people being unemployed now for 1.5 years, 2 years, trying to find something in the industry. And I don't know if it's going to get any better. That's part of the reason why I started streaming, is I don't know that AI will derail us as quickly as my brother thinks it will be, but I think the bigger influence is just, A, the economy sucks right now, but B, people are realizing that maybe you don't need 45 developers, especially ones getting paid American salaries, and you can offshore a lot of that And maybe you can still run your product with 10 developers and pay them a lot less. And it's kind of the situation we're in. And I think a lot of like the venture capitalist funding just dissolved over COVID. So it's kind of rough out there for us. But I thought once our AI overlords do take over and you can make a game in 20 minutes with an AI prompt, then our only safeguard against that is to have a following of people that like us for us and are interested in seeing the things that we make. So I'm starting the journey. But C# is I want to say it's the best language. I've recently gone from hating C++ to maybe thinking C++ might be the best language. But man, it took a really long time for me to stop hating C++. Especially if you start with C# and then transition into C++. Ooh. And I did C++ for a little bit in college, but mostly started with Python, and Python's way more forgiving, at least for the beginner, than C++. And then you get into C# and it's like, oh my gosh, this is what languages should be. The .NET framework has figured out so much for you, and if you want date times or if you want file path handling, it's just all there for you. But then you come into C++ land and you get smacked in the face. But once you learn basics of memory management, then the world slowly starts to open up to you. And then, at least for me, as soon as I kind of got a foothold, I realized I was on the cusp of understanding absolutely nothing. And then I went through a major hole of like, oh my god, I have no idea what I'm doing. And then I got another foothold and thought, okay, maybe I can figure it out. And then it's like the more you learn in C++, the more you realize you don't know. But eventually you'll get to a place where you can kind of sort of do stuff, and that's where I'm at now. But if you ever have any questions, just let me know. Are VSTs like the Cal talks about VSTs? Are they the programs that you put into a DAW to make like synths? Is that approximately right? Nice. Do you know what a stylophone is? My son is obsessed with this guy named Joe Porter on YouTube, and Joe Porter plays a bunch of different instruments. He'll go from like a marimba to a steel pan to a aquarion to boom whackers, and he just plays like little bits from different video game music or something on each of the instruments. But he has something called a stylophone, and I'm pretty sure I'm gonna get that for my son for Christmas, because it's like I can only describe it as an analog synth. It's like a tiny little, I'll just show you. I want one really bad. Oh, this one's too fancy. This is what I'm looking for. This is also way fancier. Yeah, here we go. I want one. All right. What was that? Oh, yeah. Okay, so now we have So this file here contains the C++ representation of the structs that we put directly into the shaders. And we've put delta time here. We're going to also need to put it in the shaders and pass CPP. So this is actually the HLSL code here. And you'll see that we have a representation for each of the structs that we have on the CPU side of the house. And the syntax for HLSL is really similar to C++. So what I'm looking for is removing one of these floats for padding and adding a float for delta time. So the last thing I need to do is, now that we've made the data type to hold the float for delta time on the CPU side, now we have a container for it on the GPU side. Now we actually need to update it with data. And we do that in front end. Where did I put that? This will be the fun part. It makes the most sense. So this is our main render loop. And what we do is we build all of our render states. So that's anything. This is our scene to GPU interface. So in our scene we have objects that have meshes, they have materials, and all of that. I'll show you a scene. So we have, let's find a good, you can set a skybox, which is in the old graphics. You can set your camera and move it around. And you can, we have something called an ECS, which is an entity component system. And that allows you just to store kind of an efficient collection, kind of a graph of the relationship between all of the objects in your scene. And so in this scene, we've explicitly created each of these types of objects. We have lights, we have objects that have physics interactions, we have objects that can move, and everything you can see here has something called a mesh renderer attached to it. And then the way that those get into the shader is in NC Graphics Impl, we have a concept of render state, which takes the ECS and then grabs all of the data that the shader needs, transforms it in some way that makes it into the shape that the shader needs to read from, and then it's magic. Then we just process whatever math needs to happen in the shader to get a final color per pixel. Okay, so I never can find how we get the time, but I think it's a global constant. So if we do const auto equals what do we include for that? Where do I want it in here? So now I'm just doing the variable propagation game, setting things from the main run loop for rendering into the render state here. Actually, I'm gonna put that at the end. You know, it's a global, so maybe it makes more sense just to... No, I bet I'll end up needing it elsewhere. All the time. Okay, so now it's in front-end render state. Okay. Is that everywhere I need to wire it up? I could look, or I could just build and let it find out for me. For now, definitely every Wednesday at 8:30 till like 10-ish, 10:30. So definitely every Wednesday, and then occasionally other days depending on when the kid goes to bed. But yeah, join me, and if you ever have any questions about C++ or just anything, send them my way. Oh, of course, the tests. My toxic trait is never, ever updating the tests, forgetting they exist until they yell at me. The best thing I can tell you is, if you're beginning your programming journey, is learn about unit tests and learn about the idea of, it's called TDD, but test driven development, because getting in that mindset early on will save you years of heartache. It's a really good practice. The idea is that before you start writing whatever function or whatever class you're trying to write, think about it in the terms of, what are the units of behavior that I want this thing to do? And if you get that really well defined, you can actually write little unit tests that, because you don't have any functionality written yet, your unit test will fail, but you can write out little unit tests of what you expect the behavior to be, and stub out little methods that don't have any implementation in them for your function or class or whatever you're building. And then as you build out your class, you can be constantly running your tests until eventually they all pass. And it's kind of an inversion of thinking, but it's really, really useful. And no, I never write my unit tests before I write my functions or classes, but thinking about your class in the context of how will this be tested makes you think about things like dependencies, and generally gets you in a good state. But that's called TDD, or test driven development, and I'm very pro TDD. You do take 3 arguments. What? My other toxic trait is saving while the build is in process, which building with MSVC never was an issue, but now that I'm building with Ninja, it seems to be an issue more and more. Yeah, TDD is one of those things I feel like everyone says they do it as a best practice. I don't know if anyone actually does it by the book, but it's useful in the sense that it frames the way you write your code in a way that makes it testable. And testable code is good code. But maybe the best way to learn the lesson that testable code is good code is to write code that you then try to add unit tests for and realize you have to do a bunch of refactoring because maybe you have statics in there that muck with things, or you can't easily mock something out means to have like so when you're unit testing, you only want to test a precise bit of functionality. So if you have a really complicated system, you want to be able to mock out or stub out so that it's just dummy code, everything but the unit that you're testing. And if you've written your code without unit tests in mind, that could be an absolute nightmare trying to detangle that. Okay, so we have the time in there. Let's see if it actually did anything. Let's see if we can change the color over time. there's something I have to do, and it probably is going to bite me here too, but I can't remember what. But there's something I need to do to actually get the delta time to update, and I never remember what that is. Maybe it's seconds since last. Let's see it used elsewhere. The worst is when you run into a problem that you literally solved 4 or 5 weeks ago and you've forgotten what you did to solve it. So you have to go through the exact same process. Happens to me on the reg. Let's just see if that does any. Okay, made everything darker, but it's not changing because I need to accumulate the delta time. I think that's what it is. But how do I do that in a shader? Oh, I can. Okay, this might be wild. Oh yeah, I think that's what I have to do. So what I'm doing there, so delta time is the time since last tick. So it should be, we're targeting 60 frames per second, so it's going to be a 16th or a 0.001 of a second. And what you can do, you can use that value if you're incrementing it every frame. It gives you a steady tick. So if, for example, if I were just to instead of driving this off of delta time, if every single frame I just incremented elapsed time by like 0.001, you're not necessarily going to get a consistent increase. So time at delta time, because it's capped at your frame time, you can actually use it to it a frame rate independent time. I think I explained that very poorly, but it's because I've never understood it very well. All I know is that it allows you to represent the passing of time in a shader or anywhere you want to use it. So we should have some light strobing now. And we don't. Let's bump you up a little bit. There we go. So we are brightening the color. And then as soon as we get to 10 seconds, then we darken again and we slowly go up. That's kind of neat. Okay, so phase 1 of Compute Shader is complete. What did I say that I was going to do? Oh yeah, we want to now, in a Compute Shader, move every transform by some random bit. A transform is just the position, rotation, and scale of a mesh renderer. So the goal here, and a mesh renderer is just the component that... How weird. Why are you black now? Isn't that interesting? Weird. So what we're going to do is, in a Compute Shader, for every single object in our scene, every frame, we're going to randomly translate it just a little bit each tick of the time. And this is just a dummy test to try to get a Compute Shader working, because I've never done that before. But once we get our Compute Shaders working, then we're going to be able to do some really cool stuff. Largely culling, and culling basically means telling the telling the GPU what not to draw. So if you see it, well, I'm losing my voice. Hold on. If you've ever seen a scene with just like what looks to be hundreds of thousands of objects in it, the GPU is probably only rendering a tenth or maybe up to a third of those objects, and it uses very smart math to be able to decide what it doesn't have to actually draw to the frame, because every draw is expensive. For every draw, you have to, for every pixel, do some kind of calculation, maybe a lot of calculations before you can decide what that final pixel is going to be on the screen. And so the less of that you do, the better. So occlusion culling is what I'm going to be trying to work on, which apparently is the hardest one, but true to form, I usually pick the most stupidly difficult things to work on first, and then everything else becomes much easier. But the idea of occlusion culling is, so something occludes something if it hides it from view. So if you have, let's just say 10 cubes, but they're all in front of the camera, so you have 10 cubes descending away from the camera, you really only have to draw the first one if you're looking dead on, because the other 9 are hidden by that first one. So I'm going to be using a compute shader and some kind of fancy algorithm I haven't learned yet to be able to let the renderer know, hey, these 9 aren't visible to the camera. You don't actually have to waste the time to draw them. So that's why we're going to build up to having a compute shader. But first we have to figure out how they work. Okay, so the easy part is done. Now we need to change the buffer that holds all of our transform matrices to be shader writable. That is in component source signature. Oh, and now we need our first instance of parameterizing this guy. So when you create a buffer, and a buffer is just a container that can be accessed on the GPU, it's just a bucket that holds data. When you create a buffer, you have to decide, how is this buffer going to be accessed? Is it going to be just written to once on the CPU and then sent over to the GPU? Or is it going to be accessed in such a way where the GPU can write from it, or write to it as well as read from it? And or is it going to be, let's see, in a place where the CPU needs to write to it every frame or frequently? And typically what we do is we create a GPU read-only buffer that the CPU does not have write access to. So we'll write to a temporary buffer, a temporary bucket, all of our data. And then we do something called creating a staging buffer, which is just a mailman that can bring the CPU buffer over to the GPU. And then it copies all of the data into the GPU into a read-only state. And that's the most efficient because whatever memory container you pick has implications for performance. But when it comes to a compute shader, we're actually going to be writing back to the buffer in the GPU, which is unusual. So we need a different type of resource type. And SRV means shader resource view, which means can the shader read from this buffer? And UAV is unordered access view, which, as far as I'm learning, means the shader can write to it as well. But this is a general purpose function, so now we need to parameterize this. Never remember if you put default arguments in the header or the CPP. I think it's the header. We're gonna try it. Oh, I only want to do this for the structured buffer. Oh yeah. Culling is definitely really, really interesting. Especially once you get to see how much of what you're actually seeing on a frame is an illusion. It kind of destroyed video games for me for a while because what is that? What do they call it? It suspends disbelief. It breaks whatever that is. But I'm now realizing that maybe the reason I don't play video games is just because I'm too busy. My brother's convinced I don't actually like video games, which I do, I swear. I'm just a busy person. Are you ever in the state of hyper productivity where you feel anxious if you're not doing something that you've deemed productive? It's really hard to get out of that mindset for me. Like, oh, I'm doing something relaxing or taking care of my body. How dare I? So I'm just setting a default parameter here so that all of my downstream consumers of this function don't have to be updated right now, then I only have to update the one that I'm going to change, which will be the invocation of this through the mesh renderer buffer desk. Yeah, I've never been diagnosed, but I was just even today looking at how to get out of ADHD paralysis, which some people call analysis paralysis, but I like to call it feeling so anxious that you're not getting anything done that the only solution is to continue to not get things done. Okay, so now in component resource signature, non-shader bindings, we can pass in we need one more place. We need a resource type. So by default, these are going to be only read-only in the, they're going to be read-only in the shader, so you can't write from them, which is the use case most of the time. Yeah, I went to a therapist about it, and she said that that the symptoms of childhood trauma are really, really similar with the symptoms of ADHD, and she did not think I had ADHD when I talked to her. But I had never heard that before, but apparently depending on the attachment styles that you form when you're a kid, you can very much mirror the thought patterns and the maladaptive behaviors that someone with ADHD has, which in some sense was kind of nice to hear, because it's like, oh, that means maybe if there's not something chemically wrong with my brain, I can therapy my way out of it. And I've had greater or lesser success with that throughout the years. I've been trying to get into yoga, and so far so good. If I am in the mental state already where I can do yoga, then the rest of the night I'm just fantastic. I'm clear as a bell and calm and totally productive. Yeah, that is definitely a thing. When I first heard about masking, which you probably know about, but if anyone that's listening doesn't, masking is just trying to be perceived as normal, so you spend a lot of time, like all your spare cores in your brain are processing how to come across as a socially acceptable human being. And I've gotten so good at that I thought I was introverted, but I think really I get extremely exhausted by how many of my cores in my brain are allocated to keeping up appearances, and I'm just subconsciously doing that all the time. I haven't figured out how to turn that one off yet. So we're starting to lean towards aligning our lines by columns. So rather than just putting everything just a space after the next separator or the previous separator, we're doing column alignment, which does make things easier to read a lot of the time until you introduce a variable. And why did I put that in the middle, not at the end, like some kind of absolute maniac? Yeah, exactly. Yeah, unless the brain is on something that it's interested in, and then it's like, oh, there are the missing 14 gigs. My other toxic programming trait is, I don't know why I do this, but when I'm introducing a new field to a struct or class, I just always put it in the middle instead of at the end. And I never realized that I do this until I try to add to it. Don't do that when you're coding. Just put things at the end, or sort them by size, or alphabetize them, or probably sort them by size, but don't just throw them in the middle. It's a bonkers thing to do. And see, now I can get back to my column alignment. Look at that. Okay, so all we've done here is just make the function that allows us to specify what type of buffer we want to create a little more flexible, so that we can now control what the write and read access of that buffer type. Oh, you've got it. You need flags. All right, I think I've run out of Go juice, but come jump on. Oh, thank you. This is iteration 2, almost, actually technically this is iteration 3 of our graphics engine. You should see some of the code in iteration 2, and we don't even have iteration 1 anymore. It's been a work in progress. But when your engine gets to be, oh, this is the build directory. When your engine gets to be as big as ours is, it's learn good practices or perish. But anyway, I'm out of Go juice, so yeah, jump on next week. Very exciting to have a follower. See you later.